Alright gang, here we are with our second video for Chapter 8. This is Mr. Cheeseman back teaching you about chemical reactions, and we're going to do some balancing equations finally. So, first off, as we talk about the types of chemical reactions, there's 5 types of chemical reactions that we're going to talk about. Synthesis, decomposition, single displacement, which is also called single replacement. Freshman year, the books that we used always talked about single replacement. Our chemistry book talks about single displacement, but they're really the same thing. So we also have double displacement and combustion. So let's talk about synthesis first. So with synthesis is really joining things together. As we think of our types with the chemical reaction, we have the reactants is the thing we start with. Products are what's created. So with synthesis, we're talking about multiple reactants creating a single product. So as we think of joining things together generically, we can look at this through a generic chemical type equation. A plus B equals AB. Well, here's another analogy. We got our emaciated bird here, and then there's a big fat worm, and the bird eats the worm, and now they come together as one big fat bird. So that is synthesis, joining together. If you've ever assembled something, putting things together like that, that is synthesis. You had parts and you put it together into one thing. So, example we saw in class, we saw the synthesis of magnesium and oxygen gas. The burning of the magnesium created magnesium oxide, which is the joining of those two parts. So, like we said before, we will talk about balancing this and how the amounts of reactants will be the same as what we end with here. So, we'll get to that. So, there's our magnesium burning. We saw magnesium oxide, the white residue coming off of that. Now, decomposition is the breaking down of things. So, as we think of, it's the opposite of synthesis, really. So, we have one reactant now, and it's going to break into multiple products. Don't get stuck thinking about a number. It's not just 2. We could have multiple things break up like that, just like synthesis could have multiple things combined together. So, here's our generic equation for it. AB is one thing starting out together, and as it breaks up into A plus B. Well, a reaction analogy of that, we've got our egg here, and it's getting ready to hatch. So after the egg hatches, that's the reaction, the hatching process. Well, now we have multiple parts. We have the egg shell, and we have a little baby turtle here. But we have multiple pieces. We started off all together and things broke up, and again there's probably more pieces of eggshell around, so it's not just 2 things, it's multiple things. It may be multiple things. It doesn't have to be, it can be just 2, right? So an example of that is thinking of water. We can take water, and using electricity we can break up the water into hydrogen gas and oxygen gas. So here's an example of that with a battery. We can put this in there. We can have a test tube upside down filled with water in the beaker. And these were originally filled with water, and now as we have our electrodes put in there and the gases that are released, we see, hey, there's twice as much hydrogen as there is oxygen, because originally we're talking about H2O when we think about the ratios there. We will talk about balancing, and we will see how that will work out in the end. Now, as we talk about decomposition, there are some specific things that we will talk about in the chapter, and one of those is a carbonate. if we had sodium carbonate, magnesium carbonate, whatever we have, something carbonate, when it goes through decomposition, it will break down into an oxide and carbon dioxide. So here's an example of calcium carbonate, which is what we would also call chalk. It's from seashells. That's what they're made of. Limestone and marble, all that stuff is calcium carbonate. But when it breaks down through decomposition, it turns into calcium oxide and carbon dioxide gas. So you will probably see some bubbles coming off on this. That's a sign of a chemical reaction happening. So that's one thing specific that we will talk about. So if you see a carbonate go through decomposition, you know it should break up in this manner. Now, there is a single displacement reaction is going to have something by itself switching with something in a group. So as we think about reactants, we are starting with an element and we're starting with a compound. Remember, a compound is elements joined together somehow. And so generically we can think of that as A plus BC. So BC is together, and then A is going to displace B. It's going to kick B out, and now we have AC, and B is by itself. So our analogy here, we got Bob and Susie dancing out there on the dance floor, and we got Stan over here by himself. He's single, right? Well, now he cuts in, and now Stan is dancing with Susie, and Bob is all by himself. He's the new single person. We have a new grouping here and something else that's by itself. So that's what makes it a single displacement reaction. So chemically thinking of, we could have aluminum, and we will see a similar reaction in a lab that we will be doing. We'll take aluminum wire and we will introduce it to a solution that's aqueous. This solution is copper 2 sulfate, and this is dissolved, and so when it dissolves, it gets pulled apart into its ions in solution. We have electrolytes. So with the copper being switched out with the aluminum. So aluminum is displacing the copper from the reaction, and we will have copper all by itself as a metal. It's balanced with its electrons, so it is metallic copper, and aluminum is going to be the ion now in solution. Again, we will talk about the balancing of this, but this will be aqueous. So an interesting thing with this reaction is that the copper 2 sulfate, when it is in solution, it has that bluish color like all of our copper compounds do when they're in solution. And as we switch that out, the copper is coming out of solution and becoming a solid. So you see how the blue color gets pulled out, and aluminum sulfate in solution is clear. So as we see this reaction take place, this is sped up. It's a bit slow of a reaction, but you lose the blue coloring because we don't have copper dissolved in solution anymore. Now, this just can't happen with anything, right? You think of doing this in reverse. Well, if I had my aluminum sulfate solution introduce copper, well, it's not going to go backwards. Otherwise, we'd have a double arrow here and showing going the other direction. We have a thing called an activity series, and there is one in your book in Appendix A, and you'll find the activity series there. And for metals, we look at the most reactive metals are up at the top, and then we go down in reactivity until the least reactive metal. We know gold is not very reactive. That's why we find it in the ground pure, and we like it for jewelry. Lithium is super reactive. As we talked about, sodium we saw blow up and all that. So we look on this list, and I see aluminum right up here, and copper is down below it, way down here. And so it is less reactive than the aluminum. So metals are reactive by losing electrons. So we know that aluminum is going to be the one that's going to end up as the ion in the solution. Basically, copper takes the electrons from aluminum. If you think about what happened originally, sulfate took electrons from copper, and now copper is looking around for some more electrons, and it's like aluminum comes in there. It's like, hey, I can take aluminum, and it steals electrons from aluminum, and now aluminum's the big loser, left as the positive ion in solution. So we need to have a more reactive element as the single element introduced to our solution. If you have an element that is less reactive than the counterpart, metal for metal, non-metal for non-metal, if it's less reactive than its counterpart in the compound, it's not going to happen, and you won't have a single displacement reaction. So this activity series is important. It's probably bookmarked in your book already. If not, you'll want one in there because you'll need to flip to this every time you're looking at a single displacement reaction to see if it actually happens. Now, a double displacement, we don't have anybody single. We have two groups, two groupings, and they switch partners. So again, as we think about two compounds, and as we're looking at ionic compounds that are dissolved in water, we have a positive and we have a negative. And so positive, negative, and they're going to switch parts. So I have my A as my positive, negative B, positive C, negative D, and they're going to switch. So I'm going to get the A and the D together, and the C and the B come together. But I put them in the proper order. We always know the positive should go first. And an example of this, we can think generically here. We got Mr. Fancy Penguin, and we got the Smarty Pig here with his glasses. And now we got the Smarty Penguin, and we got the Fancy Pig. So they switched parts. We had two groupings, and they switched parts. That's the key idea for a double displacement reaction. Chemically, we can think of a solution. Silver nitrate is a great thing. We'll use this quite a bit this chapter to look for reactions. But if we combine this with sodium chloride, table salt, that's in solution. Both of these are in solution. They're dissolved in water. These both would look like clear solutions. Now we combine them, and we get sodium nitrate, which is still in solution, so it's still floating around pulled apart. But the silver chloride gets solid. And what you would see in this case is it's a white precipitate. It makes a white solid. These two stick together so well that water can't pull them apart. When something is aqueous, it's been pulled apart into its different ions, and since this is not aqueous, when these two meet up together so strongly that water can't break it up. So that solid part that is formed, we call that the precipitate. So this combination made a white precipitate. Silver chloride was the precipitate of this reaction. So that's what that means, a precipitate. From two solutions, we created a solid. Now, sometimes when you mix something together, there is no precipitate, and they're both aqueous. That is not a chemical reaction. If you did this combination, you'd be like, ooh, I got this clear solution, and I mix it with that clear solution, and it's still clear. That's nothing new being formed. That is not a chemical reaction. So our last type of reaction is combustion. Everyone's favorite because you get to burn stuff. Yeah, fire. So when we burn stuff, basically what we have is a fuel reacting with oxygen. It creates carbon dioxide gas and water vapor, always. So the fuel may be different, but those other parts are always going to be the same. So here's an example of methane. CH4 is methane. There's our nice tetrahedral shape. And we have our diatomic oxygen. And so as this reacts with oxygen, and again, we'll talk about the balancing here in just a minute, it's going to create carbon dioxide and water vapor. So we can see the quantities here. Everything is getting used. Things get broken apart and reattached together in a different manner. That's what a chemical reaction is all about. Another example is having butane. That's what's in a lighter. So C4H10. And with this reaction, we see we needed to start with 2 butanes. It takes 13 oxygen, a whole lot of oxygen is required, and we create 8 carbon dioxides and 10 water molecules out of that. So now we can finally talk about balancing equations. So the balancing of the equations, the key thing is what we call the conservation of mass. Mass cannot be created or destroyed during a chemical reaction. That means there's no missing parts, and there's no parts popping out of nowhere. So whatever you start the reaction with, you're going to end the reaction with. Just like doing laundry, sometimes you're missing a sock, but the sock has to go somewhere, right? It can't just disappear in the washing machine. It's somewhere stuck to a shirt, in another pile, or still in the hamper. Whatever it is, it doesn't just disappear on its own. To balance these equations, we're going to be putting numbers in front, kind of like we saw in that last combustion. And those numbers out front are called coefficients. So the coefficients show you how many of those molecules or atoms that we're going to be using. So as we look for reactions here and doing some examples with this, let's go back to some of the examples we saw I talked about before. If we had water, and we have liquid water, put the little L there, and we have a reaction take place, and we said that it's going to go through decomposition, one reactant, multiple products here. It's going to make hydrogen gas plus oxygen gas. Now, as you're writing these out, you very well may need to put coefficients out front here, so leave some space. Think ahead as you're doing this stuff. So as I'm looking at writing these formulas out, I know oxygen's diatomic, I know the hydrogen's diatomic, so now as I go to balance, now I'm in balance mode, and I think, what is wrong here? Well, this is really weird because I've got H2O, which we know oxygen. Ooh, that looks horrible. Whoops, there we go. Let's erase this. There we go. Okay, so we've got oxygen. That looks better. And oxygen has that bent shape. We know it's got the 2 lone pairs here that I'm not showing. But we know that there's 2 hydrogens to 1 oxygen. We have our diatomic hydrogen, which pairs up, and we have our diatomic oxygen, which pairs up. So if this is what we're making, we must have all that stuff in the beginning. So if we're starting with water, and I'm making these oxygen molecules, I better start with more than 1 water. So I'm starting with 2 waters here. And the way I show that is by putting a 2 out front. That 2 out front tells me how many of these things I am making. The subscripts that we use tell us how it's made. Water is made of H2O, 2 hydrogens and 1 oxygen. We can't just decide, well, today I'm going to make water this way, H2O2. Because that's hydrogen peroxide, and you don't want to drink that. So we can't just change things. You're not that powerful. That's nature, and we can talk about how many we have, but we can't change what water is. So as we do this, we see, oh, I have 2 oxygen. I can put those together over here to make my oxygen molecule. Now I look at my hydrogens, it's like I've got 4 hydrogen over here. So I could make 2 of those hydrogen molecules. And the way I show that is by putting a 2 out front. So this is what we would call our complete balanced equation, because it's complete because it has the states of matter in there also. And we balanced. Whatever we started with is the same as what we end with here. Let's do our other reaction we saw in class. Magnesium reacting with oxygen gas. And we made magnesium oxide. So we look here and we think, well, what's wrong? Well, I'm starting with 2 oxygens. I got my diatomic oxygen. And a little sloppy there, but we'll fix that. And there we go. And we get magnesium oxide out of this. Well, it's like, where did that other oxygen go? If this is what we're creating and I'm using all of my parts, I must be making 2 of those. If that's where the oxygen is going, then I need to have 2 magnesium oxides. That in turn means that I need to have 2 magnesiums in the beginning. I can't change how magnesium bonds with itself. It's not diatomic. We're going to have 2 individual atoms of magnesium like that. So 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens. Everything works out. Everything's balanced. So I think I can. Ooh, can I do that? Sweet. All right. So let's try another one. Let's do a single replacement. Aluminum is solid, like a aluminum wire we'll use. And let's do copper sulfate, copper 2 sulfate, sorry. And that is going to be aqueous. Now, you don't know right now how to figure out if something's aqueous or not. There are some rules we will go through, but trust me, this one will dissolve in water. So it's a single replacement. The aluminum can displace the copper, so we will get copper all by itself as a solid, and we will get aluminum sulfate. Now aluminum is a +3 charge, sulfate is a -2, so we could build these up to 6. 2 aluminums would make +6, and 3 sulfates would make -6. This is also aqueous, so we will have that solution there. So now we look at what's wrong here, what's not going to work out. When we do this, metals are a good place to start. So I should have changed my color before I did that, but we have 2 aluminums on this side, so I need to start with 2 aluminums. And now my aluminum problem is fixed. I look at my other problem here, sulfate. If you think of these things, if the polyatomic stays the same, it's a whole lot easier to just think of this as one thing. Instead of counting sulfurs and counting oxygens, just think, oh, I got 1 sulfate here, I got 3 sulfates there, I better fix that. I put a 3 out front. Having 3 of those molecules makes 3 sulfates. It also changes this into 3 coppers. And it's like, well, when that breaks up, I'm going to need 3 coppers in the end. Let's do a double displacement. If I have sodium phosphate, sodium is a +1, phosphate is a -3, so that is our correct formula. And anything with sodium, here's a quick little tip, the alkali metals never make precipitates. The only exception is lithium fluoride. Everything else will always be aqueous. So sodium is always aqueous. There's no exception of sodium being aqueous. And let's combine it with silver nitrate. And another tip is anything with nitrate is going to be soluble. So silver nitrate soluble. We mix these around. We go to the dance and they switch partners up, whatever's going on here. We're going to make sodium nitrate with silver phosphate. Silver is a +1, so it's going to take 3 silvers to 1 phosphate. So, I said before, sodium's always soluble. So is nitrate. So you definitely know this stuff here is aqueous. Now, phosphate is not soluble unless it's with something like sodium. So this is our precipitate. From 2 solutions, we made a solid. Now, don't freak out that, like this. I had 3 sodiums over here, and well, why doesn't this? Well, this is how they come. This is nature. Again, +1, -1. Silver is a +1, phosphate's a -3. That's just how they're going to come together. So we worry about the balancing after we do the formulas. I checked my charges. The charges all work out. I'm going to switch mode and get to balance mode now. So we look for something wrong. I have 3 sodiums over here. I only have 1. So I'm going to need 3 of those molecules of sodium nitrate. Well, follow the chain effect. If I put that 3 out front here and have 3 sodium nitrates, that means I have 3 nitrates also, right? So I look over here, there's only 1 nitrate. So then I change that. And then that effect here, putting that 3 out front, also makes 3 silvers. But whoa, look at that. Silver's already got 3. So now we are completely balanced and everything works out. Last one I want to show you is another combustion reaction. And with this one, I'm going to use butane. So butane is the fuel that's in a lighter. It is normally, at room temperature, it is a gas. When it's in a lighter, you see it's liquid, but it's under pressure. And you squeeze the trigger on the lighter, and you don't see liquid pour out. It's gas that comes out. So again, it's going to react with oxygen gas. And it's always going to create carbon dioxide and water vapor. So we know that's a gas, and this is going to be a gas. Gas. This is also going to be a gas. So these are the correct formulas. That's formula for water, carbon dioxide, oxygen, butane, whatever. Now I switch modes, and now I'm in balance mode. So we look at what's not correct. The carbons have 4 on the reactant side. There's only 1 here. Remember, this is 1 carbon, 2 oxygen. So if I'm going to use all of this carbon to make carbon dioxide, I better be making 4 carbon dioxide molecules. Well, we also look at the hydrogen. We have 10 hydrogens, and I'm going to use all those hydrogens to make water. Well, each water has 2 hydrogens, so I can make a total of 5 waters from that. Now, I'm going to add up my oxygen. I didn't say it before, but another tip when you're balancing is if you see something in 2 places on the same side of the equation, this is on the product side, both of these compounds have oxygen. So that makes it very difficult to try to balance that in the beginning. So do the other ones, do the easy ones, and then save the oxygen for the end in this case. The one that's split up, save that to the end. So by having 4 carbon dioxides, each carbon dioxide has 2 oxygens, I'm going to make 8 oxygens from that. Here with the water, 5 waters, I get 5 more. That's a grand total of 13. Well, we go over here and we think, well, what can I put out front that would make 13? Everything I put out front here is going to make an even number. So I could put 6.5. Now, mathematically that works, but reality is we can't have half a molecule. That's not the way oxygen comes. It's like trying to go to the store and breaking open a pack of socks and grabbing one sock and bringing it up to the counter. They're not going to let you do that. So oxygen's not going to let you do this either because it comes in pairs. So if you ever have a problem like this, you got an odd and an even. Yeah. And you got an odd and an even number. That's not going to work. Double it. If you double it, you'll get whole numbers. So I'm going to put a 2 out front here. Well, now 2 times 4 makes 8 hydrogens. So I change this, and I want an 8 there now. So 8 carbon dioxides. We'll use 8 carbons. And over here, I'm going to have to erase this, because now I have 2 times 10 is 20 hydrogen. So to get 20 hydrogen out of water, I'm going to have 10 waters. 10 times 2 is the 20. So down here, as we're looking at counting up our oxygens, 8 times 2 is 16. 10 times just 1 there, right, is 10. Well, that equals 26. So I need to get 26 out of this. So now I double that number that I had there before, and I get 13. And that works out. Everything is good. We got 26 oxygens there, 26 on this side, 8 carbon, 20 hydrogen, and that's it. Whew. So it's a good thing I have something with an eraser on it, because you are not going to get these the first time every time. Sometimes it's fairly easy. Sometimes it's hard, and you got to go back and forth and erase numbers and do that. So use a pencil, use something that's erasable, because it's going to make your life a whole lot easier as we're balancing these equations. So we'll do some practice in class and see how everything goes. Hope this went well and you didn't fall asleep. So we'll see you next time.